Next up we have section 1.3 dealing with exponential functions. Now this is a very brief section but also a very important one. First of all, we're going to talk about just plain exponential functions, and then we're going to talk about the number e. So let's dive right into it. Exponential functions. So the textbook definition of an exponential function is as follows. Let a be a positive real number other than 1. The function f of x equals a to the x is an exponential function. So we have our independent variable, our x, is in the exponent. We have a certain number a raised to the x. So we have an x in our exponent, and what that means is that we have a function that grows really, really quickly. So as that x value gets bigger and bigger, our y value grows exponentially and shoots off into infinity, basically. And if we have a negative x, if we have 2 raised to the power of the negative x, then we have a function that started off really high, sorry about that, but is slowly decaying and then bottoming out at y equals 0. Now, here we can see a little bit of the behavior of an exponential function. And please note that for whatever reason in this grapher here, the base is known as b, which actually kind of makes more sense. The base is known as b, whereas in the textbook the base was a. And we also have a plus c here. So let's see what happens when we change the base, which in this case is b. It looks like it kind of, interesting things happen. So when I change my base and I make it bigger, it looks like it shoots up at a much steeper rate. So now I have a base of 4.4, and on the right hand side over here we see that our function is shooting off much more rapidly than if the base was just at 1. Okay, we have a much slower growth there. Now, an interesting thing happens. Whenever we go to a value that's below 1, we have an opposite effect. We have now exponential decay. This thing is going down. So that's because if you raise a number that's greater than 1 to x, and as x gets bigger, y is going to get exponentially bigger as well, because you're multiplying. You're multiplying a number greater than 1 by itself over and over again, which means you're going to have a bigger and bigger number. But if I have a value that is less than 1, I'm multiplying a decimal by itself over and over again, which means I'm going to have a gradually smaller and smaller number. So it's going to be shrinking here. So again, right as I go to b is equal to a number greater than 1, I have exponential growth. And here I have exponential decay if our base value is less than 1. So let's put it back to, let's say 3, so we can see it easily. Let's see what happens when we mess around with c. When we have c, okay, so if c is a positive number, it means we're shifting our exponential graph up, and if it's a negative number, it's going down. So at c equals 0, we're having our exponential function as we go to the left. It looks like the line's approaching 0. But if c is a positive number, that means we're shifting our exponential function upwards. And if it's a negative number, we're shifting it downwards, which is not unlike a normal line. If I have a line in the form of y equals mx plus b, then that plus b is going to shift the line up or down because it's y-intercept. Now, this is very confusing, but in this case, we're going to call that, instead of y equals mx plus b, we have plus c, because we already have b designated for the base here. But yeah, so the c just shifts our graph upwards or downwards depending on what value we choose for c. And then our base governs how quickly, how rapidly our exponential function grows if it's greater than 1, or how rapidly it shrinks if it's less than 1. And if our b value is exactly 1, we just get a flat line, a constant, because 1 raised to anything is just going to be 1. Next, let's talk about the number e. This is known as the Euler number. Euler was a mathematician from several hundred years back who discovered the number e, which is one of many so-called natural numbers that kind of appear periodically throughout nature that we don't really have an explanation for. Another example of a natural number is pi, 3.1415, and so on, which of course tells us the ratio between a circle's radius and its circumference. So E is similar to that. It's a number that exists out in the universe that frequently pops up and that we see all the time in mathematics and is actually very important. And like pi, it's a never-ending number because, of course, human beings made nice round numbers, but nature doesn't play by those rules. So a lot of ratios, a lot of natural numbers are going to be never ending, like pi is a never ending number, 3.1415, and so on. And the Euler number, or number E, is also never ending. And without going into too much detail, pi pops up when we're talking about trigonometric functions or circles, and E pops up when we're trying to do a number of different things. So for example, radioactive decay, temperature change, probability theory, growth rate of money. The Euler number pops up all over the place, from things such as radioactive decay, which is a natural phenomenon, all the way to things such as finance, growth rate of interest in money. We see this number pop up in finance. We see it in chemistry, biology, and also harmonic motion, which is really important in physics, and we're going to talk about that a little bit later. But if you see E, know it's this long, never-ending number, and it's a natural number, naturally occurring number, much like pi, that we encounter all the time across various disciplines of math and science. But we're going to be dealing with E a lot for our calculus lecture series. It's a little bit difficult to wrap your head around, but much like pi, E is a natural number that pops up and that is very important. And that's going to wrap up section 1.3. Join me again for section 1.4.